Welcome back to McMaster University course, Computer Science 1JC3, Introduction to Computational Thinking. We're continuing today with the algebraic data types. Topic. So we're going to start with enumeration types. Enumeration type is a special kind of algebraic data type, and it enumerates a finite set of new values. So this type is constructed like this. It's given a name t, and then it has any number of constructors, but these constructors don't take any arguments. So we have n constructors here, and they will each represent the n values of our type t. Okay, so here's an example we've already seen. This is an example of Bool. Bool is an enumeration type. It has two values, false and true, and these two values are defined by constructors that take no arguments. Okay, so let's use this type Bool. And to do this, we're going to have this line. We're going to import the prelude, but we're going to hide Bool, false, and true because we're going to define our own Bool, false, and true. So we have our definition here, just like before, and we're going to define the function implies. And this is a binary Boolean operator. It's actually a curried binary Boolean operator. We've seen the truth table for this before, and we're going to define this operator, this function, using pattern matching. And the first pattern is right here. That's a pattern where the first argument is true and the second is false, and the value we get back for this function is false. And then the second pattern is right here. That's basically the pattern of anything else we'll get true. And this corresponds to the truth value for implies. So the important thing here is that we're defining implies using pattern matching. Okay, so let's look at another useful enumeration type. I'm going to call this weekday. This is an enumeration of the days of the week. You can see right here that I have the 7 days of the week. And now I'm going to define a function on this type called meaning. Meaning takes a weekday and it gives back a string. That string is going to be the meaning of the day. What does the day mean? Now the interesting thing about the meanings of the weekdays in English is that people have pretty well forgotten what the meanings of these days are. The first two are interesting. Sunday is Sun's Day. Its meaning is Sun's Day. Monday is Moon's Day. The next four are days of Germanic gods. And these gods' names are given in Old English. After all, English is derived from Old English, so it goes back to Old English. Old English as a language ended around 1000. After that became Middle English. So we have Tuesday, its meaning is Tuesday. Wednesday, its meaning is Woden's Day. Thursday, its meaning is Thor's Day. And Friday, its meaning is Frigga's Day. Now, I mentioned these are the Germanic gods in Old English. They have different names in Norse and in Old Norse, I should say, and especially in Scandinavian mythology, and particularly Icelandic mythology, they have different names. So, for instance, Odin is the name of Woden in Icelandic. Now, the interesting thing is the last day of the week, Saturday, its meaning is a god. It's named after a god, but it's named after a Roman god. Saturn. So it's a curious mixture of Germanic gods and Roman gods. Okay, so I have a question for you. What kind of algebraic data type is the following? What kind of algebraic data type is defined by this data declaration? Okay, so I'll give you a moment to think about that. You can turn off your video if you want. Okay, welcome back. Could it be an enumeration type? No, because enumeration types, if we go back up and see what they're like, all of the constructors have no arguments. In our example here, we have 3 constructors, year, month, and day. They each take an integer as an argument. So it's not an enumeration type. Is it a product type? No, because product types have 1 constructor. Is it a sum type? Yes, it's a sum type. Is it a synonym type? No. If it were a synonym type, we'd have to have type here. And what would be here would have to be an existing type. So it's definitely not a synonym type. Okay, so let's go back and review a bit about recursive types. What is a recursive type? Let's just go back to our definition of an algebraic type. So an algebraic type, we define a type T. It's possible for T to be one of these types in here someplace. If so, that is a recursive type, because that means we're defining T in terms of the type itself. Okay, so that's what a recursive type is. And here are some examples. The first one is nat. This is a recursive type to define values that represent the natural numbers. And if we think about this a moment, we have 2 constructors, 0 and suc. 0 doesn't take any argument, suc takes 1 argument, which is a nat. So if I write out the values, we start with 0. We have suc 0. We have suc 0 like this. And so forth. And these values represent the natural numbers. And because we have our algebraic data types satisfy no junk and no confusion, it means that there is no natural number that we can't build up with these 2 constructors. That's no junk. And there is no value that we can build up with these. There's no value that we can build up with these constructors in more than one way. Every value is constructed uniquely. That's what's called no confusion. Okay, so let's look at the second example. List integer. This is going to be a data type of all possible lists of integers. And we have 2 constructors, nil and cons. Nil represents the empty list of integers. Cons represents the construction where here we have a list and we put on the front of it another integer. So this corresponds to this notation, where this is our list of integers. Well, this in list integer is not this operator, but it has the same structure as this operator that we use for forming lists in Haskell. Okay, so let's look at another example. Bin tree float. This is a type of binary trees. Now, binary trees look like this. They're trees that branch, but they always branch in a binary way. And so we can build up all binary trees this way. And these are binary trees that have numbers attached to them, attached to the nodes. So like we could have, in this case, floats. And so forth. All the nodes are attached. And so there's two kinds of nodes here. There are leaf nodes. These are the leaf nodes. And they're all going to have a float attached to them at those nodes. So these leaf nodes are bin tree floats in themselves. And then there are also branch nodes. So these are the branch nodes. And you'll notice that a branch node is going to have a left tree, a number assigned to it, and a right tree. So the left tree, if we're looking at this branch node, the left tree is this, and the right tree is this. Okay, so let me just repeat. We've defined 3 recursive types. The first represents all natural numbers. The second represents all lists of integers. The third represents all binary trees to which float values are attached to the nodes. Okay, so here's a question for you. The set of values in a recursive type is A, always finite, B, sometimes finite and sometimes infinite, C, always infinite, D, always countably infinite, E, always uncountably infinite. So you can stop your video, think a moment, come up with the answer. Okay, welcome back. Let's just think a moment before we look at the answers about NAT. It's one of the simplest recursive types. And you can see that the values of NAT are going to be infinite. That's because it's recursive. That's because we can use this constructor to build new values out of the values we already have, and we start, in this case, with 0. Okay, so the set of values in a recursive type is always going to be infinite. But more precisely, it's always going to be countably infinite. That means we can count out the members. So here, we're effectively counting out the members. We're saying that's the 0th member, first member, second member, and so forth. So we can always count out the members. Now, it's not uncountably infinite. We can't really go in and discuss cardinality today. But every set, even infinite sets, have a cardinality. And sets that have the cardinality that's the same as the cardinality of the natural numbers, we can call those countably infinite. Sets which have a bigger cardinality, they're called uncountably infinite. And the best example is the real numbers. The real numbers are uncountable. That means we cannot count them out by saying we have the first real number, second real number, and so forth. Okay, so let's go back to this example NAT. Here it is. I've added driving show. That way we can automatically print things out the way we would like to print them out. Okay, so I'm going to define 2 functions. NAT plus and NAT times. NAT plus represents plus, and NAT times represents times. And I'm going to define both of these in pattern matching. So for NAT plus, on the left-hand side, the pattern is just X. There's no structure here. On the right-hand side, I have these 2 patterns, 0, or the successor of Y. And what this means is, since I'm representing plus, basically I'm saying x plus 0 is x. So I'm saying x plus 0, x plus 0 equals x. And then for success y, I'm saying x plus y plus 1 equals x plus y plus 1. That's basically what we have here. Now notice that here the pattern is suck y, and we're using a y here. So by structural recursion, this makes sense. And so whatever natural number value we assign to here, it's going to be smaller here. Okay, so that's how we can define plus recursively for the NAT algebraic type. Times is very similar. We have these definitions. The first one corresponds to x times 0 equals 0. The second corresponds to x times the successor of y equals x plus x times y, which we can see this is true if we distribute x over y. And we have the same kinds of patterns on the right here. Okay. Now, you know what the Fibonacci numbers are. They are a sequence of numbers where we have the first Fibonacci number, which we'll call 0. The second one, for the first one is 1. And then we start adding them. And so forth. So each Fibonacci number, except for the first two, we get by adding the previous two. So my question is, how many equations do we need to define this function by recursion? So this is a function over NAT. Remember, NAT is representing the natural numbers. Okay, so let's see what we have here. Wait, I forgot to discuss the answer. Sorry. We certainly, so let me give you a moment, if you haven't already taken a moment to come with the answer. Okay, so certainly it can't be 1 because NAT has two constructors, and we need almost always to have two patterns, because we have at least two patterns, we have two constructors. We usually need a pattern, at least one pattern for every constructor. So it could be 2, because we have two constructors, but that's not the case. We actually need 3. Here they are. So I've already gave you a glimpse of this. So we have to define the first two cases. So those are, by these patterns, the 0th Fibonacci number is 0. The first Fibonacci number is basically 1. And then after that, if we have suck of x, then we take the previous two Fibonacci numbers and we add them. That's how it's defined. Okay, now, if you remember, I said every algebraic type has a structural induction principle that goes with it. And this principle we can use to prove properties about the type. So here is the structural induction principle for NAT. And this principle allows us to prove statements of this form. This says for all NATs, or you can think of all natural numbers, the property holds. So by structural induction for NAT, what do we need to prove this? We need to prove two things. We need to prove, maybe I will put that in a different color. We need to we need to prove that the property holds at 0. And we need to prove this fact. This says whenever the property holds at some nat, it will hold at the successor of that nat. If we prove this and this, then we will know that the property holds for all p. So this is the structural induction principle for nat. Now the interesting thing is we got this principle from our definition of nat as an algebraic type. But this principle is the same principle that you may have used in high school called mathematical induction, or sometimes it's called weak induction as opposed to strong induction. Okay, so let's prove a statement using this induction principle. The statement I'm going to prove is this. For all x, 0 plus x equals x. Now you might say, well, didn't we just have that? Well, let's go back to the definition. Let me clean this up a bit so we can see what we're doing here. So this was the definition of plus. And I said the first part, the first line here was x plus 0 equals x. We want to prove something different. We want to prove 0 plus x equals x. That is different. And you could say, well, isn't addition commutative? And we know these are the same. Well, we don't know that. We don't know anything yet about nat plus. All we know is it's defined this way. We do not know if this really represents addition. We haven't proven that. We do not know if this is true here. We do not know if plus is commutative or associative. Those are all things we have to prove. And we prove these things by induction, using our induction principle for nat. So I'm going to prove just one of them, what I have here in the box. And instead of writing out 0 and success and nat plus, I'm going to use these symbols because it's more compact. Okay, so I have to prove, let's just go back to our principle. I have two things to prove. This, that's what's normally called the base case. This is called the induction step. I have to prove those two things. And I also have to decide what P is, what my property is. Okay, so here's P. P of x equals this statement. X plus, or 0 plus x equals x. And so now, for the base case, I have to prove P of 0. Well, P of 0, what does that equal? Well, if I put 0 in for x, I get 0 plus 0 equals 0. That's true by the definition of P. So we know that 0 plus 0 is an instance of this right here. This is the first part of the definition of nat plus. So we know this holds, therefore P of 0 holds, therefore we are done with the base case. Let's go to the induction step. So the induction step, we start by assuming that the property holds for x, and we have to show that the property holds for the successor of x. That's what it says right here. We're proving an implication. Well, we're proving a universal statement, so we pick an arbitrary x. Now we have to prove an implication. We assume this and try to prove this. That's exactly what we're going to be doing. Okay, so I'm going to start with P of the successor x. What does that equal? Well, I know this is what my property is, so I put in successor of x for x here and here, and I get this. I get this by the definition of P. Now I know that this is an instance of the second equation that defines plus. It's an instance because I replaced the x's with zeros. So we know 3.2 is true. And now I know that this is true by the induction hypothesis. This is essentially equal to p of x. So what I'm going to do here is, now I know this is true, 0 plus x equals x, so I'm going to replace this here with x. And now I have 0 plus the successor of x equals the successor of x. And that is this. So I've shown that. I'm done. And therefore, by mathematical induction or structural induction for NAT, I know that this statement is true. This is a very typical proof by induction. And if I was going to completely develop my facts, I would prove that plus is associative, I would prove it commutative, and then I would prove that multiplication is associative and commutative. I'd do all these proofs by induction. Okay, so we're going to stop here, and we will continue with algebraic data types next time.